So yesterday we talked about the conventions, fundamentals of vector addition. Okay, quick review. I always represent vector quantities as an arrow. The length of the arrow represents the magnitude. The direction the arrow is pointing represents the direction. Okay? When we are adding vector quantities together, we always draw those arrows in what way? Tail to head, yes. Okay, tail to head. We draw the tail of the second vector on the head of the first, okay, indicating that this one happened first and this one happened second in some cases. If they happen concurrently, that means at the same time, we still draw them head to tail, tail to head. We still draw them tail to head, okay, because we still need to get what the overall result of those two things is. Okay, we don't get that by putting them tail to tail, okay, because that just won't tell us the same thing. All right. Okay, so we are going to look at, okay, how to do that vector component addition. We did a problem at the end of class yesterday, but I think by then you were all very overwhelmed and you probably didn't process very much of it. Okay, so we're going to look at all the little bits and pieces of how we do that vector component addition today. Okay, so the first thing we have to look at is how you resolve a vector into its components. All vectors have a horizontal, or x, component, and a vertical, or y, component. Right? If that vector is angled, then we can use trigonometry to calculate how far over x and how far up that goes. Okay? And then we're going to look at how we put those vector components together to get a big picture of what actually happened during that trip. Okay? And then getting what we call our resultant. Okay? Our resultant can represent lots of different things. If I have two displacement vectors that I'm adding together, my resultant will represent my total displacement. If I'm adding two velocity vectors together, my resultant will represent my average velocity. If I'm adding two acceleration vectors together, it'll represent my average acceleration. If I'm adding two force vectors together, it will represent my net force. Okay, that we won't do till the next unit, but we're kind of moving in that direction. Okay, all right. So if I'm looking at vector A, all right, so if I'm looking at A here, okay, A goes a little bit over to the right and a little bit up, okay, as it goes along. Everybody okay with that? Okay. If I knew how big A was, and let's just say we did know that. Let's say that A is 50 meters, okay, and I knew that this angle here was 40 degrees. Would I be able to calculate AX, this red line at the bottom, and AY? Okay, so I would use trigonometry at this point. Because I know the hypotenuse and one angle, I can calculate the other sides. Right? So AX is what we would call the horizontal component, or the x component of this 50-meter vector. How would I calculate AX? Sorry.
You'd use cosine?
I'd use cosine. Okay, because cos tells me the relationship between the adjacent side, which is AX, and the angle and the hypotenuse. And those are the things that I have. I'm looking for the adjacent side, AX, and I know the hypotenuse and the angle between the two. Okay, so I would use cosine to get this, right? Because we know that cos of theta, in this case 40 degrees, is the adjacent side divided by the hypotenuse. So if I wanted to find that adjacent side, since I know theta and the hypotenuse, I would simply multiply both sides by the hypotenuse, and I would be calculating my adjacent side, or AX. Everybody okay with that math? Okay, just algebra, right? How would I go about calculating AY? Which side is AY? Adjacent, opposite, or hypotenuse? It's the opposite side, yeah. Okay, it's not touching the angle. What trig function do I use if I am using or trying to find the opposite side and I know the hypotenuse and the angle? Sine. Sine is opposite over hypotenuse. So if I wanted to get this side here, I keep in mind that the sine of theta equals the opposite side divided by the hypotenuse. Okay, since I know the hypotenuse is 50 meters, I know theta is 40 degrees, do the same thing. Multiply both sides by hypotenuse, and I'm calculating my opposite side. Okay, that is how you resolve a vector into its components. Okay, anytime you're given a vector, you'll be told the vector's magnitude is this and its angle or direction is this. From there, you can always build a right angle triangle where you can figure out how far over it goes and how far up or down it goes. Okay, everybody all right with that idea? Okay, that is something we are going to do over and over and over again, okay, in order to do vector component addition, because we're going to add those components together like we did yesterday. Okay. All right, so looking at this is what I just showed you a minute ago. Okay, to get the adjacent side, okay, I would use the hypotenuse A times the cos of theta. To get the opposite side, I would go A, the hypotenuse, times the sine of theta, and that would give me that side. Does that mean Y will always be the opposite side? It doesn't mean that. Okay, it all depends on how the triangle is drawn. Y could be the adjacent side. Okay, it all depends. Right? If I had a triangle that looked like this, let's try it this way. So if I had a triangle that looked like this, okay, this is now X and it's the opposite side. This is now Y and it's the adjacent side. Y is just always vertical, X is always horizontal. Okay. Okay, so if we had this 175 meter vector, okay, so they're telling us D is 175 meters, right? If I want to calculate X, okay, the X component of that vector quantity, I would take the angle and the hypotenuse and use cosine to get X. Okay, so we would go cos of 50 degrees times 175 will equal X. What mode does your calculator need to be in for all this? Degree. Yeah, if you haven't checked lately, check, because you'll get really wonky answers if it's in radian mode. Okay. All right, so we'll have the cos of 50 times 175. All right, so that side there is 112.5 meters. And that would be along the x-axis. It doesn't even say whether it's north or south here. Okay, and then to get y, I would use the opposite. So I go sine of 50 times 175. Okay, now, which side's longer, x or y? Y is longer. How do we know that? Besides, I can see it in the picture visually that it's longer. Is the angle more than 45? So if the angle is more than 45, it goes up more than it goes over. Okay, so it's something to watch for, because sometimes people accidentally get the trig functions mixed up, and that's a way for you to check if you've done it right. Look at your triangle and go, wait a minute, y is supposed to be bigger than x here. I must have done this backwards. Okay, it's just one of those little checks you want to do as you're going along. Okay, so sine of 50 times 175 gives me 134.1. Okay, so in following that 175 meter vector, this object goes to the right 112.5 meters, and it goes up 134.1 meters. I've just found the x and y components of that vector. Okay, you would have done exercise after exercise like that in Mountain 10 when you were doing the geometry. Okay. Okay, questions so far on finding the x and y components? Everyone's okay with that so far? Okay, so here's what we want to do with those x and y components. Okay, so in this diagram here, what we're dealing with are these two vectors. We're trying to add vector A, which I'm drawing in purple, okay, and vector B, which I'm going to draw in green. Okay, I'm trying to find the resultant. We'll say they're both displacement vectors. So I'm trying to find the overall displacement if an object follows vector A and then follows vector B after that. Okay, so here's what I have to understand about that. During vector A, the object goes over that much. Okay, during vector B, the object goes over this much. Okay? If I add those together, do I get the total amount over that object went? I do. What can that help me do? Well, it can help me find how far over that object goes in total. That is, it gives me one side of my resultant, of my overall displacement. Okay? Similarly, during vector A, the object goes up this much. Okay? And during vector B, it goes up this much. Right? So now, if I go and take those two ups, okay, put them together, I didn't do a very good job drawing them, okay, I get my total. Right? And the same is true for the overs. Okay, if I put those together, okay, I get my total over and my total up. Okay, everyone follow there? So we find the components so that we can find the sides of our overall trip, essentially. All right, so that's the whole purpose or the whole idea behind vector component addition. Find the components so you can add those components together. Okay? Now, it just so happens that this one, they're all going the same direction. All the x components went to the right and all the y components went up. Is it always going to be that way? It's not. Okay? Sometimes you're going to have the second vector does something different. And then you'll have to add them and make one of them negative. Okay? What we're essentially doing is breaking down every vector into a bunch of collinear vectors. Okay? A bunch of things that only go right or left or up and down, because those are easy to deal with. Okay? All right. So here's what I would like you to do. I would like you to write down what's here, okay? And but hold on, I want to change one thing. No, it's okay, we'll leave it. Write it down as it is, but don't worry about the diagram just yet. Okay, we're going to build the diagram here in just a minute. Just write down the question, and I'll write down the diagram in a bit. So the most important thing in a vector addition question is the diagram itself. Okay? Being able to draw the diagram helps us to kind of analyze what's happening. Okay, so drawing the diagram is the most important thing. It's also, believe it or not, the thing people screw up most often. Okay? People rarely get the math wrong in one of these questions. Okay? Most of the mistakes are made when drawing the diagram. And then the diagram throws off the math. And then when the person has done their question, they look at it and go, well, I must have done the math wrong. Okay? Because that's where we go, right? Like we have this, unfortunately, cultural thing about math is hard and I must not be good at it, which is total crap. Okay? People are innately good at math, they just lack confidence. Okay? So the big thing is drawing, which is going to be hard on you because you're going to say, come on, anybody can draw, which is also not true because I can't. Okay? All of my people, their legs come right out of their heads when I draw people. I can't even draw stick people correctly. Okay? So we always think that the drawing is the easy part, when it's not. We have to make sure we get it right. Otherwise, it's going to say something other than what our math says. And we're always innately going to trust the picture, because that's easy, over the math, because that's hard. Okay? When in most cases, it's actually the math that's right and the picture that's wrong. Okay? So, if I'm drawing this, this is the process I want to go through. Okay? Draw each vector one at a time. So kind of just draw it with me as I go here. All right, so I'm going to draw an arrow that represents my first vector. It's supposed to be 145 meters long, 70 degrees above the horizontal. Okay, so what I want to draw first is just a line that goes along the horizontal. Okay, so something like that. Okay, and then I want to draw my actual line. I want to go 70 degrees above that. That's my reference. Okay, it'd be like if I'm going north of east, I'm going above the horizontal. Okay, so I'm going to go 70 degrees above the horizontal. Okay, and then I'm going to draw in another one of these. All right, so now I've got my first triangle in there. All right, so I'm going to say that this angle here is 70 degrees. This is 145 meters long. Okay, is this side X or Y? This is X because it's the horizontal side. Okay, and that would make obviously this side Y. Okay, so that's my first vector. The second vector is 105 meters long and points 35 degrees below the horizontal. Okay, so I'm going to need a different color for that one. So I'm going to go in there and make it, I don't know, blue. Okay, I'm going to make a nice horizontal line. Okay, because again, my angle was measured from the horizontal. Chris, question? Because they didn't tell me positive or negative, I'm going to the positive X here. I mean, if I made everything to the negative X, it would also be fine. Okay. All right, and then now I'm going to put in my blue arrow. Okay, 35 degrees below the horizontal. And it's only 105 meters, so I should probably make it a bit shorter. I think I made that too long. I'm just going to shorten that up a little bit. Now, normally, guys, I do not take this kind of time and care when drawing a vector diagram. It's just the first one, so I want to make it really neat for you. Okay. So there's the triangle for my second vector. Okay. This angle here is going to be 35 degrees. This is going to be 105 meters. This side will be X or Y. This is X, it's the horizontal side, and this is Y, it's the vertical side. Okay, now, both my X's go to the right, but one of my Y's goes up and the other goes down. So I'm going to have to keep that in mind when I get to the point where I'm adding my Y's together. Right? So, where would I draw a line that represents the total displacement in this situation? Okay. This was my starting position here, okay? And the object finishes over there. So where would I draw a line that represents the total displacement of the object?
A straight line from the beginning to the end.
Exactly, a straight line from the beginning to the end. Just want to make sure I have the right arrow here. So from here to there. Okay, that line is my resultant, and in this case, my resultant is the total displacement of that object. Okay, that line also has a horizontal and vertical component. Okay, so that's my diagram. Now, was I fairly careful to represent the magnitude with the length of the line? I was. I wasn't exact, I didn't measure it, but I did edit my diagram a little bit when I was like, ooh, I feel like that line's too long. Okay, I made sure my 105 meter line is shorter than my 145 meter line. Okay, but like I said, I didn't measure it, I didn't scale this or anything. I just made sure that it at least somewhat represents what was going on. Same with my angles. I didn't measure that 35-degree angle. That angle could be anywhere between 30 and 40 degrees probably, okay? But it'll work for the diagram. Okay, so you don't have to pull out a protractor or anything like that, okay? Unless you really, really want to, but it's going to take a lot longer to draw your diagram than you do. All right, so I want my overall displacement. If I'm going to get big D, then I'm going to need to know what red X and red Y are. And right now, I have no idea what they are. So what I've got to do is piece them together from the vectors I know numbers for. That's the black vector and the blue vector. Okay? So what I want to do next then is, since I've already identified my X's and Y's, I want to calculate all my X's and Y's. Okay, so the next step here, and this is the next step in any vector addition question, is to start calculating your X and Y components from the vectors you know. All right, if I want to calculate black X, okay, it is the adjacent side to this 70-degree angle, right? And the hypotenuse is 145. What trig function should I use? Cosine, right, because that'll tell me, okay, the adjacent side in relation to the hypotenuse. So I'm going to go cos of 70 degrees, okay, times the hypotenuse, 145. All right, so that side is going to be 49.593. Meters, right, it was in meters, yeah, and that is going to be positive. Okay, everybody all right with that? I'm keeping in my calculator that number so that I have all the decimals when I start doing calculations with it. I'm just not going to write all 10 decimal places. Okay. All right, so if I just use cosine to get x, what am I going to use to get y? Sine, the other one. Yeah. So I'm going to go sine, the opposite side, okay? So times 70, or sine of 70 degrees, times 145. Okay, 136.255. Meters, and that is also positive because I'm making up positive. Okay, so I now know these two sides. Okay, this one's 45.5, that one's 136. Okay, can I do the same thing for the blue triangle? Yep, and I have to, Okay, I need to know what blue x and blue y are, so that's my next set of steps. Okay, so blue x is the adjacent side to the angle they gave me, and I know the hypotenuse, so same deal. I'm going to go cos of the angle, in this case 35, times the hypotenuse, in this case 105. All right, so that side is 86.01 meters. And that is positive because it's to the right, just like the other one. Okay, blue y is the opposite side, so I use sine to calculate that one. So sine of the angle I was given times the hypotenuse that I was given. Okay, so that comes out to 60.226. But that one's negative because it points down. Okay, so now I know all the x's and y's except for my resultants. But can I get them now? Okay, I can get my resultants x's and y's now because if I take black x and I add it to blue x, does that give me red x? Okay, so that's what I want to do next. Okay, my next step is get my resultants sides. Okay, so that's going to be black x plus blue x, which is going to be 45.593 plus 86.01. And this is where I want to go back to my big numbers with all the decimals. Okay. Oh, I put in the wrong number there, guys. How come no one caught that? That's supposed to be 49. Okay, gotta fix that. This is 49. Okay. So take those numbers and add them together. So I'm going to go up here and get 49.59, and I'm going to add it to the 86.01. Okay, so red X is 135.6 meters long. And it's positive. Red Y is going to be a little bit different because blue Y goes down and black Y goes up. Okay, now I did make blue Y negative, so I'm okay to still do vector component addition. I'm just adding a negative number, which in your calculator you're totally fine to just subtract. Okay.
Would you be able to just, like, not make the blue y a negative and then subtract it?
That's what I just said, absolutely, yeah, okay? You can just subtract and just recognize, okay? Usually in a question when we're doing this, these are gonna have compass directions. And so instead of writing positive and negative, I'm gonna write north, east, west, or something like that, okay? And then I'll have to go, all right, I have to subtract west from east. Okay, so for y then, I'm going to take my black y, 136.22255, and I'm going to add negative 60, or just subtract 60.226. Alright, so my 136 minus the 60. Gives us 76.03. Meters, and that is positive, because we still end up from where we started. Okay? Everyone okay with that so far? what can I do now that I have the two sides of my overall displacement? I can find D. Well, how do I do that? I use Pythagorean theorem. If I know the two sides of a right angle triangle, I can use Pythagorean theorem to get the magnitude of D. Not the direction, but the magnitude. So that's my next step. Okay? I'm going to calculate what D is, the magnitude of D, by using Pythagorean theorem. So 135.6 squared plus 76.03 squared. Once again, keep all the decimals. All right, I'm going back into my calculator and fetching all those decimal places when I punch this in. Okay, so square root of, okay, that number squared, right, plus that number with all the decimals squared. Because it makes a difference. I mean, if you're squaring that and you abbreviate a bunch of decimal places, it makes a difference. Okay, so the magnitude of D is 155.46 meters. Okay, what's left? What else do I have to find? I gotta find the angle, because displacement's a vector quantity. I need magnitude and direction. So I'm looking for theta. Theta is my direction. I know all three sides of the triangle. How do I go about finding that angle? Yeah, inverse of whatever trig function you want at this point. You calculated all those sides. There's no, better value to any one of them. For me, I like 10. It's my favorite trig function. Okay, so I always use it. Okay, opposite over adjacent. But you could use sine or cos. Okay, just use the appropriate sides to get that angle. Okay, so for me, I'm going to go that theta equals tan to the minus 1. Tan is opposite, so 76.03 over adjacent 135.6. Okay, and again, I'm using all those decimals there, guys. That gets me 29.28 degrees. And what vector was I given in the question? Above the horizontal, below the horizontal. So everything refers to the horizontal. I can't put compass directions in here. I wasn't given compass directions. All right? All I can say is that this angle right here is above the horizontal. I would say I could probably be even more specific. If it were me, I probably wouldn't write above the horizontal. I would write above the positive x-axis. Okay? Because the horizontal does go positive and negative, and if I just say above the horizontal, that doesn't specify which direction. Okay? All right, how many significant digits should my answer have? 3. Okay, everything in here had 3, right? 145 has 3, 105 has 3, both angles have 3, right? So my final answer, right, should end up being this. The overall displacement is 155 meters at 29.3 degrees above positive x-axis. Is there another vector that could also be correct here? Which one? Okay, yeah, that one is one of the two correct ones. Is there another correct one? We drew the triangle this way. Is there another way I could have drawn that triangle? I could have also gone like this. Are those the same? Other than it drew little arrows there when it wasn't supposed to. Okay. Those two triangles are the same, they're complementary, right? The only thing that's different is this angle isn't going to be 29.3 degrees above the x-axis. It's going to be 60.7 degrees. Okay, right of the positive y-axis. That would also be, it's the same direction. It's just going to refer to the y-axis instead. You could have drawn either one of those triangles and gotten the same answer, but with a different direction. Okay? All right, did that take quite a while? But did I go pretty slow? Okay, and I meant to. Okay? And as we get better at these, they go faster. Okay, but you kind of hit kind of a top limit to how quickly you can do one of these. There's a lot of steps. The good news is, it's always the same steps. Okay? Draw the diagram. Label all the x's and y's. Calculate all the x's and y's. Get your resultants triangle. That means add the x's and add the y's. Okay? Use Pythagoras, do trig. Okay? 6 steps every time. Always the same 6 steps. Okay? It doesn't matter how many vectors you get. Okay? It's always the same 6 steps. You just have more vectors to calculate the x's and y's of. So on a unit exam, am I going to give you a 5-vector question? If you say yes, you're going to hurt my feelings. Okay? I'm not that mean. Okay? Can I tell whether you know how to do this with a 2-vector question? Then that's all I need to ask. Okay? And in fact, I always, on a unit exam, give one that is angled and one that is either horizontal or vertical. So you don't have nearly as many x's and y's to calculate, because if one of them is horizontal, it only goes over. It doesn't have a triangle for you to figure out. Okay? So it'll be a little bit shorter. Okay, so this is all the written stuff for what we just did. Okay, so we're not going to bother going through it because it's what we just went through. Okay, try this one. I want you to calculate the x and y components of this 100 kilometer an hour, 25 degrees north of east vector. Yes, you can. Okay, so if I want to find Vx, what trig function am I going to use for that? Cos. It's the adjacent side to the 25-degree angle, right? So Vx is going to be the cos of 25 degrees times 100 kilometers per hour. All right, so we're looking at 90.6 kilometers per hour. And that'll be east. All right, and then to get Vy, I would use sine, because it's the opposite side. So sine of 25 times the hypotenuse, 100 kilometers per hour. And so 42.3. Oh, wait, we only have 2 significant digits. 42 kilometers per hour north, and this would be 91 instead. Okay? Everybody all right with calculating the vector components, x and y? And just finding the sides of a triangle using trigonometry. Try 1 and 3 here, guys. They're only asking you to calculate either an X or a Y. Okay, you just have to figure out which one by drawing the triangle. Okay, you don't have to do number 2 because that uses the rectangular coordinate system, which we don't use. Okay, so on question number 1, okay, they tell us a hiker's displacement is 15 kilometers at 40 degrees east of north. What's my reference direction? North, okay, because it says we went east of north, okay? So I draw a reference line that goes north and I go 40 degrees east of it. Okay, 15 kilometers. Okay, they want to know what the north component is. So do they want X or Y? They want Y. Yeah, Y points north, so they want the north component, right? What side is Y? Adjacent or opposite? It's adjacent. It's touching the 40-degree angle, right? So I'm going to go cos of 40 times 15 equals Y, okay? And I will have my 11 kilometers north, okay, for that vector. Okay, everybody follow there? Again, the biggest trick here is getting those triangles drawn correctly, okay? The second direction is always our reference. East of north, draw north. Go east of that, okay? All right, how many people have done number 3? All right, I'm gonna give you a couple more minutes on number 3, and then hopefully we'll go over that before special bell goes. Okay, let's quickly look at number 3. So a snowmobile travels 65 kilometers, 37 degrees east of south. So I draw a reference line south. I go 37 degrees. No, that's not 37, but get the idea. 37 degrees east of that for 65 kilometers. Now they want us to find X or Y? X. They want to know how far east. Okay, so that'll be sine of 37 times 65, okay, and that'll give us our 39 kilometers east. All right, we will be continuing to work on that, but in the scale of a big problem with more than one vector tomorrow. Okay.